All right, hi everyone. Welcome back to another, LTSPICE tutorial. This time we covered transient simulations last time. This time we'll be covering frequency responses, which is basically how your circuit would respond to inputs with different frequencies. And to do that, we can actually just reuse our circuit from last time if you don't know how to make it. Here's a shortcut guide on key shortcuts that you can use to build this really quickly. But you'll notice that we have the transient simulation directive from last time, as well as the AC directive for our voltage source last time. We're actually going to go get rid of this transient, so I'm going to right click, go to edit, and go to delete, because LTSPICE doesn't work if you have two directives running at once, so it's best to just delete the one you were running previously and make a new one. All right, so if you have this circuit made, just right click this voltage source and it should take you to go to the advanced section. If you're on Mac, your interface might look a bit different, but what you're looking for really is this. You're looking for the small signal analysis, or the .AC simulation. And so what you're going to do here is you're going to put 1 for AC amplitude, 0 for AC phase. And the .AC analysis method works by essentially inputting in the sine wave of the amplitude and phase you specify, which is 1 and 0 here. And it sends a sine wave at various frequencies as your input for your circuit. And from there, you can measure how your circuit changes over time with various frequencies. So a frequency response simulator, basically. And if you've ever had to do this in lab, you'll notice that this would automate the process a lot faster and give you a bit more of a theoretical output rather than a practical one, but gives you an idea of how you would expect your circuit to respond. So go ahead and click OK. And as you can see, if you did it right, you should see it over here in the AC 1 and 0. All right, so that's our simulation. That's our parameters. You can keep these parameters as you wish, or change them to the frequency to the parameters you desire. Because if you change R and C values, you change the cutoff frequency, and so on and so forth. So after you set up your parameters, you're going to go ahead and click S, or type S, press S, excuse me. And actually, while you're on that, I'm going to go make a comment real quick, because your simulation runs like this. So this is the format for a .AC simulation that more often than not you're going to be running. So .AC tells us that we want to run a frequency analysis. DEC stands for decade, which tells us basically our x-axis. We go from, if we're doing decade, we go from 1 to 10 to 100 to 1 kilohertz, and so forth and so on. All right, so start frequency and end frequency. These are self-explanatory. This tells LTSPICE basically where you want to start your simulation and where you want to end. A good habit I like to have is that you let start frequency equal 100 times less than your cutoff frequency, and similarly your end frequency more than your cutoff frequency. So why do we do this? Well, one, this is just to make sure that you're getting enough of your circuit. You're seeing how your circuit responds over a wide enough range, because whenever you're doing frequency response simulations, you'll notice that circuits actually change very little if you change the frequency a little at a time. So you would need large magnitudes of frequency changes to actually see noticeable amounts of differences in your circuit. So which is why we do 100 times less and 100 times more. At least I do it because I think it's a good habit to actually see the response of your circuit in its entirety, because too little or too much will give you a lot of redundant information, or not enough information in this case if you're doing a lot lower than your cutoff frequency. So yeah, if you have 100 times less and 100 times more, good resolution and a good response output is what I like to say. All right, sweet. All right, so with that in mind, let's go ahead and get started. So if you're still following along with this circuit, go ahead and type in .AC, DEC, 100. Also forgot to mention that 100 denotes the points per decade. So if we're doing a decade sweep, in between 100 hertz and 1000 hertz, LTSPICE will take 100 points from your circuit of responses from your circuit. So the more points you have, the smoother your curve is going to be, but the more time it's going to take for your simulation. So what I recommend doing is 100 points gives you a pretty smooth resolution. And if you're doing smaller frequencies, you can always be more precise and add more points. Just know that it will take more time. All right. So .AC, decade, and 100. And for this one, we'll make our start frequency probably, I don't know, is it 10? And we'll be safe and do 100K. I think that's fine. And you can always do greater than 100 times. If you're doing your start frequency, you can go lower than 100 times less. And if you're doing your end frequency, you can go greater than 100 times more. Think of it like I guess like a bare minimum cutoffs for your, or bare minimum ranges that your frequency should meet. All right, sweet. So with that in mind, we click .AC, click OK, and you should be able to move it around like so. Feel free to place it anywhere. And similar to before, you can run it as expected. I'm not muted, am I? Sweet, no. All right, you can run it as expected. Click run. And if you do it right, you should see this. So if you look at the output of your capacitor, which is where you're going to be taking the output. Remember, we're looking for voltage, so you're looking for the red probe, not the current. This is a current probe. So I would recommend looking at voltage. There we go. So you can see here, sorry, the previous simulation from last time still ran, so it just overrode it. And yeah, so now here we can see that we have a frequency response output. It's in bright red. And you can see the standard pass band, stop band, and you can see that our simulation runs from 10 hertz to 100 kilohertz. And you might be wondering, well, if I'm trying to run the simulation, I want to see where my cutoff is, which is usually in your -3 dB point. I repeat, your -3 dB point. You can click the title, which brings up a table that looks like this. And as you can see, it basically automatically goes to your -3 dB point, which turns out to be 100 hertz. So yeah, this should be a relatively shorter video just because you should have the circuit built already, and we're kind of building up on our tools based from what we learned last video. So now you have, you can see the -3 dB cutoff here, which we can verify that it was in fact basically 100 hertz, excuse me, 1000 hertz. 1000 hertz. So I did do the cutoffs just right then. Sweet. So with that in mind, yeah. So here's your -3 dB point, and then you can analyze any other point in this circuit as well, which you can follow along. So this solid line here is your frequency, is your gain on your, which is defined by your left axis, and your phase is defined by this dotted line, this kind of faint line over here. You might not be able to see from there, but you can kind of see hints of it. And it's defined by the right axis, which is in degrees. So just things to note that if you wanted to interpret it, you would analyze gain using the left axis and phase on the right. And you can analyze the -3 dB like so. And you can do this for basically any filter you need. And this doesn't just work for low pass filters. We can switch out R and C for high pass filters, as long as you're taking the output where you want to take the output, which is more often than not going to be around at this node over here, regardless of whether or not that's a resistor or capacitor. But that could also vary per filter. So yeah, this is an AC simulation or frequency response simulation that you can apply to any filter. And I hope you get some good use out of it. So cool. And I think that's all I want to cover for this one. This one's pretty straightforward. So thanks for watching.